Hello everyone. So as for the continuation of our topic regarding the higher order differential equation of the topic linear homogeneous differential equation with constant coefficients. So we have discussed how to identify the linear homogeneous DE and how to use the differential operator as well as the auxiliary equation, or how to transform this equation into auxiliary equation. Okay, so this linear homogeneous differential equation has have three cases. So for this topic, we will discuss the case one, or the auxiliary equation or characteristic equation of distinct real roots. Okay, so for case one, if we have, say, let the roots of m sub 1, m sub 2, up to the m sub n of the auxiliary equation are real and distinct, then we have these solutions for our differential equation. So y1 is equal to e m1x and y2 is equal to e m2x, and up to the y sub n is equal to e m n x. Okay, so this linearly independent of the real O line. So this one here is the linearly independent of the whole real line. Thus, if we get the general solution, we have the y is equal to the arbitrary constant 1, e to the m sub 1x plus e to the m sub 2x plus until such time that we have the arbitrary constant e m and x, where again the uh, m sub 1 here, m sub 2 up to the m sub n here are the roots of our auxiliary equation. So to further discuss this, let's have an example. So let's find the general solution. Find the general solution of this given DE. Okay. So say our given DE is the second derivative of y plus 2y prime minus 3y is equal to 0. Okay, so the first thing that we need to do is to write this differential equation into differential operator D. Okay, but before we apply that, of course, you need to verify if the given solution is linear homogeneous differential equation in order for us to apply this method, of course. Okay, so we have the second order, first order, and minus 3y here. So we have a coefficients, and this equation here is linear homogeneous differential equation, right? Because this is linear and this is also equal to 0. Okay, so again, we need to get the differential operator. So we have d, since this is in the second derivative, so we have d squared plus 2d minus 3y is equal to 0. Okay, so after we convert it into differential operator d, okay, we need to transform this one into an auxiliary equation. Auxiliary equation. Okay, so we say that the auxiliary equation is the equation in D. So this is already our auxiliary equation, is equal to 0. But instead of writing that, let's use letter M. M squared plus 2m minus 3 is equal to 0. So now we have our auxiliary equation. Okay, and in order for us to determine the general solution, we need to determine the roots of this auxiliary equation. Okay, and then after we get the root, then we will use this general solution and get the answer. Okay, so we have the m squared here. So we are expecting to have two roots. Okay, so we need to do some modification here. Let's by factoring. So we have by factoring this form. So we have say m plus 3 multiplied by m minus 1 is equal to 0, right? Then if you check this 1, that is also, of course, must be equal to this 4, right? Okay, so this, by factoring, we have m plus 3 and m minus 1. So to get the root, we need to equate this equation into 0. So first, we have m plus 3 is equal to 0. Therefore, m is equal to negative 3. So, so we have this root 1. So we have m is equal to negative 3. So next for this part, so we have m minus 1 is equal to 0. So therefore, m is equal to 1. So we have another root, which is m is equal to 1. And as you can see, uh, negative 3 and positive 1 as our root, so they are distinct from each other. So we have two distinct real roots. And since we have two distinct real roots, so we can use this case 1 to find our general solution given by this form. Okay? So now, by using our answers as root 1 as negative 3 and our root 2 is equal to 1, we can now say that our general solution for this given differential equation is, so we have y is equal to our first arbitrary constant 1, so we have c1 e raised to our first root, distinct root. So we have negative 3 and then variable x. And then plus c sub 2 e, our next root is 1. So we have 1x or just write x. So that's it. So this is now our general solution for this given differential equation. Okay, so once again, we need to first check if this is qualified as the linear homogeneous differential equation, and then we get the differential operator and then convert it into auxiliary equation m, then find the roots. Okay, so since we have second order here, so you expect to have a two roots. So we have m is equal to negative 3 and m is equal to 1. And we substitute it to, use the general solution. Y is equal to c sub 1 e, then raised to the first root x plus c sub 2 e raised to the negative root times x. So now, this is the general solution for this given higher order differential equation.